Okay, well, thank you very much for the invitation, and Chris, thank you for the introduction as well. So I'm going to be talking about higher field strength, pushing the limits, and the premise of that drive. How do I advance this? Maybe this. Okay. Premise of that drive to higher magnetic fields is really explained by this slide over here. We all know that the brain operates over a very large spatial scale, going from whole brain networks to mesoscopic scale organization. You've heard a lot about that from the last lecture, and to microscopic scale, where we have neurons, synapses, etc. So when fMRI came into existence, it very rapidly actually evolved to be able to map whole brain networks and activation in the supramillimeter, 2 or 3 millimeter spatial scale. But we were very much interested, I was very much interested in asking the question actually whether we can reach the mesoscopic scale with fMRI. And we developed really 7 Tesla to be able to do that. Using 7 Tesla, in fact, after a long effort to tackle the challenges of imaging at high magnetic fields, we were able to demonstrate that you can map these orientation domains together with ocular dominance columns, as shown over here. And the mesoscopic scale organization, let's see if I have a cursor, that you see here is a cartoon depiction, in fact, of the orientation domains and ocular dominance columns in the visual cortex. Now, those columns they are not really, uniform. It's not just like every single cell is doing the same thing. You have layer differentiation, so the scale actually goes finer. And we are very much interested in pushing the ability of fMRI to go into in the direction of microscopic scale. So we launched the effort of developing a 10.5 Tesla because of this. And it was, it actually, this system was, the efforts started in 2008, and we finally got approval, FDA, and got images at 10.5 Tesla approximately 2017. But I want to, before I go on, I want to mention that it's really, high fields are not just for high resolution. Many people may think, okay, it's just we are trying to do high resolution imaging, but ultra high field fMRI is not all about high resolution for imaging cortical columns and layers. I mean, that is one potential way of getting at that. But really, what high fields give you is signal to noise ratio, and in many cases, for functional imaging, for example, gives you increased contrast to noise ratio, and those are your currencies. I mean, you can use them to do high resolution. But you can also use them, and then there are many examples of that, to increase reproducibility, reliability, robustness of your measurements at any resolution. And as I mentioned, there are many examples of it, but maybe for this workshop where there's quite a bit of talk about AI, I can bring this to your attention. At CMRR recently, Kendrick Kay and Thomas Neseleris has generated this huge natural scenes data set for a massive 70 fMRI data set to bridge cognitive neuroscience and artificial intelligence. It's producing a lot of papers from this data set, but it was acquired at 1.8 millimeter resolution and relies on the sensitivity that is available for fMRI at 7 Tesla. So the rest of my talk is really quite a bit about all the things that we encountered, the challenges in going to higher fields at 10.5 Tesla, and how do we capture this signal-to-noise ratio? I want to remind you that signal-to-noise ratio in MRI in general has been a topic for quite a long time. And there's this paper by David Holt and Paul Lauterbur from 1978, where they concluded at the end, I mean, that's actually a very interesting paper, but for many, many reasons, but let's just focus on the highlight, what I highlighted, the line here, number 4 conclusion, where they said sensitivity increases with frequency to the 7 to the 4 power, like square, at frequencies below 1 megahertz, but only linearly when the sample losses are dominant, like in MR imaging, when you put a human body into the scanner. And then Edelstein and Glover and etc. In fact, later on, when they started working at 1.5 Tesla, they were able to show that this is indeed the case. This is the paper they published. They showed a linear dependence of SNR to be zero. But when you go to these very high fields like 7 Tesla and beyond, things get a little bit more complex. For example, let's look at this figure where we have a sphere, dielectric and conductivity properties approximate the human brain, and the sphere was imaged with a birdcage coil at all of these different field strengths. So you can see that the signal is actually dying when you go to higher fields, except in the very center, those blue regions. Essentially this SNR is getting less and less when you go to the high field. It turns out that this does not mean really that at high fields you are losing SNR. It's really a property of the fact that when we are at these high fields, we are in the traveling wave regime. And in this particular coil and in this particular symmetric phantom, there are a lot of destructive interferences of B1 fields everywhere except in the center. So main conclusion really is reaching conclusions on SNR based on experiments are really difficult. And this has been something that has been plaguing the field for a while. And so it's very, in fact, helpful to talk about ultimate intrinsic SNR, a concept introduced by Hocalı and Atalar in 1998. But the data I showed you comes from a recent paper that we published in collaboration with Neurospin in France and Maastricht Brain Imaging Center in Maastricht, and where we realized that, okay, we all have the same birdcage coil. It's a coil that Siemens provides for checking the instrument quality, etc. And this was a sphere that was then built and filled in Neurospin, and then it traveled to the different sites to observe to measure these things. But as I mentioned, here in this particular sample, you cannot look at any place else other than the center for signal to noise measurements, and that's what we did. And so here is the data, and you can see that in fact SNR goes approximately as a power of 2. It's a square, and we then did also make contact with ultimate intrinsic SNR using the paper from this from the NYU group, and also David Holt had some calculations for a sphere like this. In fact, that was the sphere was chosen so that we can make contact with those 2 papers, and then the result was in agreement with the experimental data. So that's wonderful news for of course high fields, where in the center of a brain where we can expect something like that. Now we work a lot with Ricardo. You've seen him many times about in this 10.5 Tesla effort that we are pursuing, and he also did ultimate intrinsic SNR calculation in human brain models, and then he also showed that in the center it goes something like the squared, and then in the periphery it goes linearly with the magnetic field, as shown by these plots over here. So how do we capture this? And obviously the birdcage coil is not a very good one to capture that. And of course, the approach we took, which is is done a lot in MRI these days, is to go to these arrays. Now at high fields like 10.5 Tesla, we don't use single transmit channels. It just doesn't work. We have parallel transmit, of course, and then this is a coil which shows you it's a 64-channel receive array with a 16-channel transmitter. It's a very interesting transmitter, but this is not what I want to talk about today, and rather I will focus on the receive array performance. So we built the same array for 7 Tesla and 10.5 Tesla, and you can see these are images in a human head-like phantom with appropriate electric properties, and you get these SNR gains in the periphery. In the center, we expect this based on these simulations and the data I showed you. But when we looked at this data more quantitatively, and we are now looking at sort of shells, thin shells, we're averaging over the shell, and the size of the shell actually shrinks, ultimately going to a point in the center. So when we looked at that data for the 64, we actually had a 32-channel coil, also at 10.5 Tesla, but we compared it to the industry standard Nova coil. We didn't build one ourselves, but the 64-channel array is identical. And what we see is that in the periphery, you meet the expected gains of a factor of 1.5, but in the center, we were really falling short of that. So we launched a simulation effort. This is again in collaboration with Ricardo and Bei Zhang, who used to be at NYU. And Bei is here, and she had a poster on this yesterday, and she's now at UC West. And so we took the coils that we built, and then modeled them exactly, and then she simulated data, and Ricardo's team, calculated ultimate intrinsic SNR. So what the main conclusion from this paper was very interesting. So when you look at 70, for example, with these coils that we built, you capture approximately 90% of the ultimate intrinsic SNR, but the same coil captures approximately 60%. Now, these numbers may be off a little bit because there are all these things that go into the simulation and noise models, etc. But essentially, the important point is that the same coil simply doesn't capture as much of the ultimate intrinsic SNR at 10.5 Tesla. So we pursued some avenues then to capture that. Okay, you need probably more number of coils or different type of coils. So we actually turned our transmitter, which you see here, into a receiver as well. This transmitter, I said I'm not going to talk about it very much, but I should mention that it looks like a loop, but it's kind of like a loop dipole type of coil. And then we built TR switches and preamplifiers built into the triage switch as you can see. And then with the 80 channel, then we captured much more central SNR, as you can see in this data. And the same, every coil has to be FDA approved at 10.5 Tesla. Then once we got the approval, we were able to show that the same is true at 7 Tesla. It may be difficult to appreciate, if you just look at the periphery, but which grows in red. But if you look at the center, for example, it goes from 7 Tesla, 32 channel, 7 Tesla, 64 channel, and then 10.5 Tesla in the center over here. Now, we are also very much interested in higher channel counts, and you saw a picture of this coil. This is a 16-channel transmit, 108 channel receiver array at 10.5 Tesla. And then with these coils, then we were able to obtain the following SNR data using those shells that I mentioned to you. These are these concentric shells. And going from the periphery to the center, you can see that the 64 doesn't do very well. 80 captures much more in the center. 128 is even more. And so if you put quadratic and linear gains, now we are talking about essentially capturing some of these SNR gains that we expect from both Ricardo's calculations as well as the paper I showed you that was conducted in collaboration with Neurospin. So major conclusion is, I would say, is that when you're working at greater than 10 Tesla, it is not straightforward to compare the SNR obtained with the same type of coil, which was the simple approach that we took initially. Same type of coil at 2 different magnetic fields. I mean, the same 64-channel array, captures a lower fraction of the micro ultimate intrinsic SNR at 10.5 Tesla. So for a head size object, more coil elements and/or different type of elements are needed clearly to approach central ultimate intrinsic SNR at 10 Tesla. And I'm sure this will be the case for magnetic fields like 14 Tesla, which is now an effort that has been launched in Netherlands. For the periphery, we all know that smaller and more loops are in general better. So not only the field comes into play, but how you detect it is also important. So such loops are in general better as long as, however, you stay in the sample noise dominated regime. So this is a figure courtesy of Jason Stockman that was given to us They published it recently in this paper in MRM, and they published the data with the 3 Tesla and 70. So that comes from them. And then we imposed on their figure the data for 10.5 Tesla and 16.4 Tesla. And as you can see here, when the loop diameter gets smaller, for example, for 128 channel coil, I mean, you're tiling it over a surface area that's more or less constant. Okay, varies a little bit from individual to individual, but it's a constant surface area. The loop diameter gets small, and with a 128 channel coil, 7 Tesla is still acceptable. 3T is not acceptable. You get more noise there. And then for 10.5 Tesla, you can see that actually you can go to smaller loop diameters, like 20 millimeter. And for 16 Tesla, which is data may be relevant for our Netherlands colleagues, but it's also relevant for us because we do animal experiments at 16.4 Tesla. You can actually really go push this to smaller loops. However, going to those smaller loops and then building these arrays like the one you saw is indeed challenging and problematic. And let me illustrate this a little bit. When you actually work with these RF coils, at some point you need to develop accurate electromagnetic models, and you have to then validate them experimentally to set safe operational limits. Now, you don't have to do that at 7 Tesla in principle. I mean, you really should do it. But for 10.5 Tesla, it's an absolute requirement because every single coil is requires FDA approval, and we have to send that data to FDA. And we were able to, do this very, very accurately. It's published in this paper that I'm showing you for a simple 8-channel dipole, bump dipole. And in 220. Then we obtained the very first images for brain images at 10.5 Tesla. Again, it turned out to be relatively straightforward when we were working with transmit and receive arrays. These are dipole arrays used in our lab for body imaging, and 10.5 Tesla. Many of you may not know that at high fields, imaging the human body is a major challenge, but because of this multi-channel transmit technology, it was relatively easy to accomplish these body images that you see at 10.5 Tesla, and the coil went through approval of the FDA process without any problem. Really excellent models, excellent agreement with data. But when we're talking about these arrays, multi-channel receive arrays inserted in a different transmitter, the problem became more complex. So I'll illustrate that with this data. So when you look at these B1 fields, so mapped as flip angles here, you take the transmit alone in a phantom, again mimicking the electrical properties of the brain. You get some B1 field distribution, and you put the receiver. Now the receiver has all the loops, but none of the electronics, and they're open circuits, and the loops alone don't make a difference. But you put the 64-channel array, and all of a sudden, everything changes. And changes asymmetrically. It is not as if it's a uniform reduction of the one field, which would not be a problem, but it's, it is, there are localized differences. Something like that, you really, have a hard time now. How do I set my safe operations limit? And because just modeling the transmitter will not be easy, it will not be enough. And modeling the 64-channel array with all its electronics is virtually impossible. So we took a lot of, did a lot of work. How can we reduce these interactions and many steps? For example, we miniaturized our preamplifiers. So they are now quite small, and they are used on coil. Their surface area is small, reducing the interaction. However, these coils are built to go into a head gradient. Space is tight. We couldn't use on-coil preamps throughout the coil. So we had to use off-coil preamps. They are larger, but we pulled them out of the transmitter so that when this thing slides in, they would be out of the transmitter. And then this mess that you see here, essentially these are cable traps, and they are every lambda 16. We had to put these cable traps in, to kill sheet currents that would be induced by the transmitter. And it actually, it looks like a mess, but nevertheless, it did accomplish quite a bit. And these are some data. And you can see, for example, here, experimental B1, transmit B1 maps and simulations, and they look much more in agreement, but they are not perfect, they are not perfect. And this would not pass muster actually with FDA. So we developed actually a method, even though they look pretty good, developed a method then to calculate an error based on these maps. And with that error calculation, then we can actually set the safe operation limits, and FDA was in agreement. So now you're talking, you can say to me, okay, Kamil, you're thinking of what, 256 channels, etc., because you can really take advantage of these at high fields. However, that really requires major developments. And my philosophy or view has been that maybe to give you an analogy with the cell phones, that the coils we have been building more or less is like this, the very first cell phone, and he's the inventor of that, developed by Motorola. And so maybe with a coil like this, we came to something like the Nokia phone that I'm showing you here, but we really have to go to something like the Apple's iPhone. Now, initially, I have to admit, when I prepared this analogy for a site visit we had, and I put the coil, this coil, really I made the analogy so that this coil was like this particular phone over here. And I was saying, well, maybe we won't get to the Apple phone, but maybe we can get to Nokia. But our electrical engineers, especially Gregor Adriani, who was here, objected to it. He said, come on, Kamil, I mean, you can at least put our coil equivalent to the Nokia. So it's however, we have to get there. That's a long path ahead of us. There's a lot of planned improvements on how we build these coils and how we can service these coils, actually. I mean, if the preamplifiers blow up in these very hard gradients that you drive to obtain functional images, and then how do you get access to this coil? But a coil should not be just this a piece of art and one-time demonstration of what you can do. But we want to use this coil day in and day out. So we are working on that. But in the meantime, I want to show you some results that we got from this coil at 10.5 Tesla. These are some SWI images of the brain, multi-slice. It covers the whole brain. I'm just showing you some slices. These are whole brain EPI images. Now, those of you familiar with EPI, I mean, EPI is used a lot in functional imaging, and they are really difficult images to obtain. They have a lot of problems with them, and the difficulty gets really much higher when you work with higher magnetic fields, 7 Tesla, and worse at 10.5 Tesla. So, they are crappy images, but these are really good crappy images for 10.5 Tesla. And we are very happy to see them. And in part, of course, it comes from the fact that we are using a 128 channel coil, and the acceleration you get from these are now just straightforward parallel imaging, GRAPPA, no deep learning. We work on that quite a bit as well, but not yet here. And you can see there are some nice results. And you can go to higher acceleration factors. This is iPad 6. Of course, SNR drops quite a bit because you are not collecting as much data. And but look at the fact that these frontal lobes, which are normally really distorted in EPI, are now at 10.5 Tesla even looking normal. Just an example of fMRI data with that. Now, I don't have yet really fMRI data like this one here, which is obtained at 7 Tesla, but shows you the power of resolution. This is like 0.5 millimeter isotropic resolution at 7 Tesla. And those of you who are familiar with fMRI or functional imaging may appreciate the fact that the activity is really nicely contained in the gray matter. And across the gray matter, you can actually see the layer-dependent activity because the input layers are coming to layer 4 in primary visual cortex. This is a retinotopic stimulation, and you can see the boundary there as well. Now, we'll get to that next conference, I'm sure. But in the meantime, I want to tell you a little bit, and I will wrap up with that, about the fact that, okay, we are pushing this, but we are also interested in pushing that, because they can actually overlap in that mesoscopic scale. And the information then, in fact, if you can do that, in principle, you can say, well, I can go from single cell recording all the way to whole brain networks. And we put quite a bit of effort, many problems, but we were able to achieve this recently. And at 16.4 Tesla, doing simultaneous in vivo 2-photon, there are 2-photon right now, in vivo 2-photon imaging and fMRI at 16.4 Tesla. So 2-photon, of course, allows you to do volumetric as opposed to just using, for example, single photon. So you are seeing essentially the focal plane scanning the images over here. And this is a single plane. You know, you can see these little things. These are blood vessels, image with a dye in the blood vessel. You can see the individual capillaries going through the, individual red blood cells going through the capillaries. And the fMRI voxel for something like 16.4 Tesla is like 250 micrometer isotropic. And that's the size of an fMRI vessel. So this is sort of very exciting, because both in terms of modeling what the fMRI signals are doing, now you can actually see every voxel, what kind of a blood vessel contribution it has. And for those of you who may not be familiar with functional imaging, I mean, blood vessels play a very important role in fMRI. And, but of course, we are not just interested in the blood vessels. You can detect with, in this case, GCAM, neurons, and you are looking at two neurons that are sort of fluctuating. This is a spontaneous activity. And you can do fMRI together with this 2-photon acquisition. I'm just showing you a single plane fMRI and 2-photon. They were obtained simultaneously, not one after another, but really simultaneously. And so you can actually look at average bold trace, you can look at average calcium trace, or you can look at individual responses of individual neurons. So we are actually excited not just about the 10.5 Tesla, which we are applying for human imaging, but very much excited in this. These are mice studies. We're going to migrate them to non-human primates. And we expect that the combination of all of these efforts coming at the problem from one end versus the other end will ultimately give us quite a bit of knowledge. Of course, I showed some of the names and people who were involved in this work, but CMR is a very large group of people, and a lot of different talents have to be brought into play to achieve those results. The engineering group is a very important one. They are shown here because many of these instruments are one of a kind, and we developed quite a lot of hardware for them and to make them happen. I did not get a chance to talk about image reconstruction, but this is, of course, really just like emphasized in this workshop, a very important part of our effort. And then the optical imaging and fMRI together, coming from CMRR. It's in collaboration with investigators in Purdue University, and these are the individuals who have done that. I will leave you with this particular slide from Paul Lauterbur, and I put this in here in view of what Dan was showing at the very beginning. And he said, well, I cut it out a little bit to make it shorter, but it said, expert watched in amazement as scientists and engineers pushed instrument performances to ever higher levels at ever-increasing magnetic field strength. I believe that it is these trends that will characterize the next decade of this field, coupled paradoxically with the emerging field of ultra-low field MRI. That's Paul in 2006. Thank you very much for your attention. And
we have time for one question. Go ahead, Jason.
Hi, thanks, Kamil. You pointed out the importance of RF development for pushing the limits at ultra-high field, and you mentioned one bottleneck that we've also encountered at MGH, which is preamp availability. It comes up again and again and again, different field strengths, different vendors. Do you think it's time that we as a community bite the bullet and design an open source preamp that will take away this barrier, maybe for the next I2I hackathon, for example, and just solve the problem once and for all? Or will the differences at different frequencies and on different vendor platforms be too hard to overcome to standardize this?
Very good point and a very important point. And I know that you use Siemens preamplifiers, for example. They are very large boards, and we source the preamplifiers just from another source, so we can build our own boards, and they are much smaller. But really, we have to go beyond that for sure. And this is an effort that we are undertaking right now. It's an interesting concept. I didn't think about that. I mean, you pioneered maybe there are others who did that, but having an open source design for these things with your amplifiers for these gradient coils, yeah, I think that's an excellent way to go.
Thanks. Kamil,